Compressed helium, produced using screw oil-filled compressors, oil separators and adsorption purification devices, is used across various industries. Their primary use is in generating compressed helium, which is then used as a working fluid in variously designed cryogenic systems. In variously designed cryogenic systems, ranging from those using traditional cycles with pre-cooling and expanders, to others designed as cryogenic machines, operating based on the reverse Stirling or Gifford-McMahon cycles. In this video, we'll delve into the technological process implemented in the compression block, using a basic pneumatic hydraulic circuit, which shows the typical configuration of the compressor block. This frequently used setup is ideal for compressing helium for major expanders or condensers within magnetic-based accelerator complexes, employing non-titanium superconducting coils, cooled by submerging the cables in liquid helium, as well as using a flowing method to circulate the helium through a nickel-copper tube with an external diameter of 56 mm at the heart of the superconducting cable. Let's explore the technological process behind the operation of the compression unit. Helium is dispensed at a rate of 1 kg per second or 21,630 normal cubic meters per hour from pressurized gas holders, maintaining a pressure not exceeding 1.05 bar and a temperature about 26 degrees Celsius, close to ambient conditions, and then passes through the mechanical cleaning filters marked F1 and F2, then drawn into two identical screw-type, oil-filled compressors of the first compression stage, designated kilometer 1 and kilometer 2, where the geometric volume changes between the drive and driven screws, compacting it along their rotational axis to an absolute pressure of 5.3 bar. All screw-type oil-filled helium compressors are classified as volume displacement devices with an open stuffing box design, where the lead screw shaft features an open cantilever and is connected to the motor's shaft through a flexible or another type of coupling. Excessive heating of machine components, such as elastic seals, intensifies helium leaks and reduces the overall efficiency of the compression process. To boost the efficiency of the compression process and lower the operating temperatures of compressor parts, screws, suspensions, seals, etc., position 2/3 along the screw axis from the suction port, cooled to about 28 degrees Celsius by a water oil heat exchanger, from position MO1 with a flow rate of about 36 cubic meters per hour at compression pressure, resulting in minimal hydraulic losses at the oil separator, position OM1, and the cooler position MO1, approximately 5.2 bar absolute. The optimal oil operating temperature for long-term machine use is between 92-98 degrees Celsius. Under these conditions, the standard alert setting for helium temperature at the end of the compression process is 105 degrees Celsius. The emergency threshold is 110 degrees Celsius. To seal gaps between screws and casings, as well as to internally cool helium, an oil based on standard paraffins is used. Ecosana HS20 and Octacosana HS28 with includes antioxidants and stabilizers like phenol. The machine is approved for use with a specified oil if the helium temperature at intake is above 0 degrees Celsius. The maximum operating temperature of the oil is 120 degrees Celsius. Currently, newly released imported helium machines use synthetic polyalphaolefin and perfluoropolyether oils. About 56% of the heat from compressing the extracted helium is dissipated into the environment from machines with vertical fins. Compressed helium, around 98 degrees Celsius and 5.3 bar pressure, moves into the oil separator. At position OM1, the oil is efficiently removed. Oil from the separator is channeled into the water oil heat exchanger at position MO1, cooling it to about 28 degrees Celsius. It is then injected into the machine's working chamber at approximately 3.8 bar. The oil flow rate is gauged by the helium's temperature. This is measured at the output instruments TT1 and TT2 from compressors kilometer 1 and kilometer 2. This flow is controlled by regulators at positions B4 and B7. A side glass in the oil circuit allows for monitoring foam intensity, in addition to the integrated oil injection system. In the compression block, it includes a circuit with an oil tank, BM1, featuring forced oil circulation, using a rotary pump, position N1, with an electric drive for cooling and lubricating bearings. It also supplies oil to hydraulic accumulators G1 and G2. The oil tank setup, BM1, enables cleaning of oil from mechanical particles by circulating it through filter F4. The de-oiled helium is then directed into the water helium heat exchanger, OH1, where it cools. Cooled to about 28 degrees Celsius using the water from the recirculation loop and air cooling units. The supply of recirculating water to the air cooling units of the compression block is the responsibility of the operating company or the unit's customer. Parameters of the recirculating water, like flow rate, are provided to customers as technical specifications. If required, the recirculating water circuit can be supplied along with the compression unit during the unit's operation. In the cold season, gel and oil coolers labeled OX1, OX2, MO1, and MO2 are fitted with three-way valves with electric actuators and temperature sensors to bypass the coolant when its temperature falls below the normal level of about 10 degrees Celsius. At this temperature, the oil viscosity rises sharply, reducing the effectiveness of sealing gaps, ensuring the compression unit operates smoothly and reliably, regardless of the season or ambient temperature. It's beneficial to include extra cooling, maintaining a steady temperature of about 16 degrees Celsius, using the water from the chiller's intermediate circuit. The evaporators in the vapor compression refrigeration system are cooled. The nominal thermal load on the chiller's intermediate circuits handle around 65 kilowatts for a helium flow rate of 1 kilogram per second as a refrigerant used in the circuits of vapor compression machines that use screw compressors and with frequency control, either R407C or R134A. Chillers located in the machine room through the intermediate circuits circulate softened technical water instead of a glycol solution. Helium cooled to about 16 degrees Celsius at a medium pressure is sent for compression into the second stage screw oil-filled compressor at position kilometer 3, where, due to a change in geometric volume between interacting screws, compressed along rotational axis to a pressure of 24 bar. This is at the second stage screw oil-filled compressor at position kilometer 3. Shares the same technological characteristics as the first stage compression compressors. 2/3 from the suction window. Along the screw axis, a water oil heat exchanger, cooled to about 28 degrees Celsius, is injected into device MO2, flowing at about 31 cubic meters per hour, under compression pressure, with negligible hydraulic losses, within the oil separator, and cooler at approximately 21.6 absolute bar. The compressed helium, with a temperature of about 98 degrees Celsius and a pressure of 24 absolute bar, goes into the oil separator, OM2, where it is effectively separated from the oil. Oil is directed from the separator to the water oil heat exchanger, MO2, where it's cooled to approximately 28 degrees Celsius, and then injected into the machine's working chamber at approximately 16.8 bar absolute pressure. The oil flow is determined by the outlet temperature of the helium at the outlet, using the TT4 device from the kilometer 3 compressor and regulated by the V22 flow controller. Helium purified to a mass concentration of about 500 ppm is directed to the OH2 water helium heat exchanger, where it's cooled to around 28 degrees Celsius by the recirculating water and from the air cooling unit. Additional helium cooling is recommended, cooling it to about 16 degrees Celsius, using the chiller's intermediary circuit water in the water helium heat exchanger, cooled igniters of the vapor compression refrigeration system. After the final cooling phase, helium from the unit compression is at a temperature between 16 and 28 degrees Celsius, and has a pressure of 23.5 to 24 bars absolute, is channeled to a unit with two sequentially linked adsorbers. The first adsorber the helium encounters includes initial filter to remove oil droplets and aerosols. This process reduces the oil concentration in helium from 500 ppm to 1050 ppm. Both adsorbers contain layers of granulated activated carbon for purification. The mass concentration in both adsorbers drops from 10 ppm to less than 0.1 ppm. Deep oil removal effectiveness relies on the helium's inlet temperature at the adsorber. Therefore, additional cooling using the chiller's intermediary water circuit is a technically sound solution. When the helium temperature at the inlet increases, and it enters the adsorber at 16 degrees Celsius, sorbent capacity from 0 to 20 degrees Celsius. This will lead to a 510% average decrease in oil sorbent capacity. Oil concentration will rise to 0.5 ppm. maintaining a constant sorbent layer thickness, due to warm adsorbers using activated carbon. In gel and rheogenic systems, it is not economically viable to regenerate them. The sorbent capacity then sets the operational lifespan of the adsorption module to at least the expected duration of a campaign at a facility that uses compressed helium. In certain scenarios, it's advisable to implement a system comprising parallel connected adsorption units with a manual control block in practice before embarking on a prolonged operation of a facility processing compressed gels. Only the first adsorber in the flow line is replaced. Typically, there's no oil bypass through the second adsorber. After extensive oil removal, the compressed gel is sent to storage units and then distributed to users. If the storage capacity of the receivers is ample, additional cooling of helium using the intermediary water chiller circuit is not advisable if the receivers are of small volume and solely function to dampen pressure fluctuations. In such systems, water-based cooling of helium through the chiller's intermediate circuit is technologically sound. That concludes our examination of the compression unit's technological process. In the next video, we'll move on to modeling of the compression unit in the Aspen HYSYS software suite.